However, testing is something that if you want to go into software engineering or pretty much any sect of computer science, you will spend your time writing test cases or testing your code in a way that we talk about that is similar to the one we will talk about in class. And if you don't, you should probably rethink the company that you are at, because testing is an integral part of your code. Okay, yellow chalk today. Testing is ubiquitous, expensive. It's not unusual to spend 30 to 40% of the project effort on testing. I had an internship 2 summers ago where I spent 100% of the time on testing, and it was terrible. Testing is not a fun thing. It's very fun to build the code. It's not that fun to test it, but it is very important so that you don't have code which does not work, which is the worst. Especially for like life critical systems like flight control. Boeing probably should invest a little bit more money into their testing. And a lot of the times it's more expensive than all other software engineering activities combined. A lot of jobs will hire specifically for people testing their code. So yeah, it's an important skill to know. How big is big? A Boeing 787 Dreamliner has about 6.5 million lines of code, and not one of them prevents the door from flying off occasionally. Microsoft Windows 10 has about 50 million lines of code, and then the claim here is that a modern car has about 100 million lines of code, though that is highly dubious. Maybe a Tesla with all of its neural networks, but yeah, code bases are big, and it's easy to mess up in your code. If you have one bug, you obviously don't want it to accidentally set the accelerometer on your Tesla to 1,000 instead of 100. That would be bad. Best practice is to test individual units or components of a software. This is known as unit testing because it's a lot easier to test small versions or small parts of the main component, say testing just the steering wheel or testing maybe just Windows PowerPoint as opposed to testing the entire thing. So you start at the base level testing individual units, and then you put those together, which is known as integration testing. How do you make sure that the steering wheel integrates correctly with the wheels and the axles on the base of the car in order to make it actually move? And then finally, testing a whole end user system is known as system testing. We will be focusing specifically on unit testing because the programs that we write in this class are typically a lot smaller and typically made up of individual units, individual methods that you write. So we've been spending the first part of this class writing a lot of methods. Now we're going to be writing a lot of test cases for those methods. This is the kind of testing we will do in this course and the next. They're called unit under test. So if you have a method like increment, the unit under test would be the increment method. Okay, so what does it mean for a program unit to be correct? Here is a claim that I'm going to make. I'm not going to draw anything on the chalkboard. When you are testing your code, you are not testing to prove that it is correct. It is impossible to prove that a method is correct. If you have, say, an increment method, and you write a bunch of test cases that see if it works when you pass in 0 or 9 or 1,000 or 1,000,000, you will never be able to, unless you're looking at the code for increment, be able to tell me if that increment method is correct. Because what if I did something like if this dot equals new natural number 48789 2. And then if it is, then it just sets the natural number equal to 0. This dot copy from 0. You're obviously probably not going to have a test case that tests for 487892 in the code, the user entering that. But if the user enters that, then the code will be false. Increment will not work. So the claim I'll make is that you are not trying to prove that your code works in every single case. Instead, you are trying to prove that it is mostly correct, that it is good enough to ship off to the user. Because you can't write test cases for every single possible input that the user could enter into the program. It's just not feasible. So it does what it's supposed to do most of the time, and it doesn't do what it is not supposed to do. How do we know what a method is supposed to do? Well, this is where design by contract, again, comes in clutch, saves us. We look at its contract, which is a specification of its intended behavior. This is a good graph for if you're thinking about testing. Say Venn diagram of sorts. This big circle is everything that can happen according to your contract. So if you look at the increment method, it says that it enters in a natural number and it increments it by 1. So something that could happen, for this code is that you enter in 1 and the resulting value is 4. Or you enter in 47 and the resulting value is 48. Something that couldn't happen is you enter in 4 and then the result is 6. That is not allowed based on a contract. And then you have actual behaviors of the method, which is what actually happens in the method body. For something like increment, the can happen and does happen will probably be a concentric circle. I think that's the word, where everything that can happen and everything that will happen is usually the same thing because there's not multiple results for stuff that can happen. However, let's use a more prevalent example, which is the one that I think they use in the slides, which is, okay, legal input, allowable result. Okay, the example that they use in the slides, which is a factor, which takes in an integer n and just returns whatever, it returns a factor of the integer. So the formal contract specification of that is that if you take the integer that you pass in and then you mod it by the resulting a factor, which you get returned, you should get 0 because the remainder will be 0, meaning it is a factor. So the simplest way that you could implement this in your code is by, okay, n divisible by a factor. I hate when the slides have little intermediate steps. Okay, simplest way is just to return 1 because a number mod 1 is always going to give you a remainder of 0, which means that it's always a factor. Is this method body correct? Well, we can look at the allowed behaviors of the method, which is something like this. If you pass in 12, an allowed behavior of the method would be that the resulting value is 4, as 4 is a factor of 12. An allowed behavior could be that it returns 6, because a resulting value of passing in a factor of 12 could be 6. It could also be 12. And it could also be 3. What it could be is something maybe like 11, because 11 is not a factor of 12. It could be something like 8, because 8 is not a factor of 12. But for the code that we have written, so what actually happens is when you put in 12, it results in a value of 1. So that's what actually happens based on the behavior of the method. So it forbids 12 and 5 because that does not fulfill the contract. It fulfills 12 and 6 because 6 and 12, or 6 is a valid return result for a factor of 12. And then we get into the actual behavior. Since we're just returning 1, the actual result of the method is in there. So what you want is you want for the actual behavior of the method to be a subset of the allowed behaviors. So something that would not be good is if, say we have our example over here, and what actually gets returned when you pass in 12 is something like 13. So that's what actually happens. However, that is not a subset of the behavior that can happen based on the contract. It's a violation of the contract. So our Venn diagram bleeds out a little bit. That would be an example of proving that your code does not work, because what actually has happened is different than what can happen legally according to the contract. Okay, so as a reminder, if you write that a class C implements I, the Java compiler checks that there is a method in I. So for each method in I, that there is a corresponding body in the class C. However, it does not tell you whether or not that method is correct. So if you have some interface I, which has 3 methods, foo, foo1, and foo2, then you have a class C, which implements that. This implements, it makes sure that you have a method body for foo, you have a method body for foo1, and you have a method body for foo2. However, Java is not that smart yet. It can't read contracts and then read the method body of your foo, foo1, and foo2 classes, or foo2 methods, and check whether or not they match the contracts of the interface. That's up for you to do. And the way that you do that is through testing. Okay, how can you decide whether this is the case for a given method body? Well, you use testing. Testing is a technique for trying to refute the claim that the method body is correct for a method contract. So I'll say it again. The goal of testing is not to prove 100% that your code works for all cases. In actuality, the purpose of writing test cases is to try to break your code. So there's a little bit of like inside of you, there are two wolves kind of thing. When you're writing the contract, you're trying to build good quality code, and then you have to take on like an evil persona, and you have to try to break that code down by writing test cases that you think will break your code. Because if you try as hard as you might, when you're the evil version of yourself, to break the code that you've built and you fail, you can be pretty dang sure that the test case that you have wrote is correct. As a tester, you want to think about defecting the test or defecting the method. So design and coding are creative activities. When you're actually implementing methods, testing is a destructive activity. You're trying to break the software. Very often the same person does both coding and testing. They say this is not a best practice. I'm going to override that and say that that's I'm not going to say stupid. That's not the best way to describe it. Oftentimes it probably should be the same person doing the coding and the testing. And oftentimes it is in industry. I see the example, or I see the argument, though, that you should not be the one testing your code if you have built it, because you sometimes want an outside perspective, but oftentimes you will be the one that's trying to break your code. And again, there comes that split personality. You have to think about you versus evil you. You have to become paranoid and malicious. You have to start sweating thinking about breaking your code. It's surprisingly hard to do. People don't like finding out that they made mistakes, but making mistakes is important. Because if you write a test case that gives you the example like here, where your actual output is not something that can happen, then you could fix it and your code will be better for it. Okay. A clear distinction should be made between testing versus debugging. The goal of testing is to show that by executing it, it might have a defect, i.e. at least one situation in which the actual behavior is not an allowed behavior. So your Venn diagram is a little bit bleeding off page. The goal of debugging is given some source code that already has a deficit to find and fix it. So the goal of testing is to find an error. The goal of debugging is to fix that error. So usually testing comes before debugging, and debugging only happens if your test cases fail. Okay, here is that example that I drew up on the board. However, it is much more pleasantly drawn. The circles are nicer. Okay. If actual behaviors are not a subset of the allowed behaviors, and we start trying some inputs and observing some results, one might lie outside the allowed behaviors. And then you would know that your method body is not correct. Because going back to this design by contract principle, you are violating the contract. You want to link, you don't want this. This is bad. Any questions so far? Going once, going twice. Sold to slide 33. Okay, if this happens, testing has succeeded in revealing a defect in the method body, and you can go back and you can change it so that your test cases run. Speaking of test cases, what are test cases? I'm going to erase this. Is that okay? Yeah. Okay. So in order to test your code, you need what are known as test cases, where you have a predefined set of inputs and outputs that you know should happen based on the method contract. And what you essentially do is you test your method code, or your code's method, or the code in your method, to see if the expected output and the actual output are the same. And these test codes come in 3 different flavors. There are boundary cases. There are routine cases. And then there are challenging cases. And spoiler alert, eventually you're going to have to write test cases on your own, and you will have to have all 3 types of test cases in order to have a valid test suite. Test cases that do not reveal a defect in the code do not help us refute a claim of correctness. Test cases like that last one, i.e. the one that succeeds in revealing a defect in the method body, should be cherished because they show you that your code is incorrect and can be improved upon. Okay. Now, a set of test cases, so boundary, routine, and challenging, for a given unit is called a test plan or a text fixture. If the actual behaviors are a subset of the allowed behaviors, we start trying some inputs and observing results, then we will never find a defect. However, we cannot say for certain, again, that the method is 100% correct unless we tested every single actual or allowed behavior of the method contract versus is expected, but that would be highly pedantic. If you had like a method that was add 1 to an integer, you would have to check all values from negative 2.147 to positive 2,147,000,000. And I'll tell you right now, that is not a good way of doing things. So don't do that. And here is a quote by Edsger W. Dijkstra, who is like LeBron James in the computer science community. I'll say he kind of did everything. Program testing can be used to show the presence of bugs, but never to show their absence. And if he's saying it, then it's probably true because he invented like everything. Not everything, but most things, a lot of things. You'll see his name definitely come up. All right, so designing a test plan, you need your boundary cases, you need your routine cases, and you need your challenging cases. I'm going to give you some life hacks for determining what your inputs and outputs should be for boundary, routine, and challenging cases. For boundary cases, you always want to look at the contract and you always want to look at the requires clauses. Boundary cases are always going to be on the boundary of what values your input variables can be. So the boundaries of the input variables. So if you're writing a method which takes in a natural number and it requires that the natural number is greater than 0, the boundary case for that would be testing, say, or I guess greater than or equal to 0. The boundary case for this would simply be a natural number or inputting a value that is 0. That is the boundary on the values that can actually be inputted to the program. So you should probably check it. Now, routine cases are going to be what the method is typically used for. So, another example, let's say that this is an increment method, which just adds 1 to the natural number. Contract should go above, but an increment method that requires that natural number is greater than or equal to 0. What are the things that people are going to be using this for? Well, I don't know. They might add 1 to like 84 or like 32. Just typical examples of how people might actually use the code if it were to function in the real world. Usually these are the easiest of the three because it's just whatever you can think of. Challenging is probably the hardest thing to write test cases for. I guess the name is quite fitting. But these are things that, given the nature of the method, might be challenging. Might give your program trouble. So, for example, an example of a challenging test case for an increment method might be 9, because you have to, if you're writing a recursive solution, deal with the carryover. So it's not just adding 1 to whatever the last digit is. You actually have to make a new digit. Could be like 99. Technically, all the 9s are like examples of things that are challenging. But if it works for like this, then you can be sure that it probably works for all of the 9 cases. Boundary cases, smallest, largest, or special values. If, say, the increment method was on an integer and required that the integer was greater than or equal to 0, a boundary case would be both 0 and as well the integer limit. So making sure that it's handling the case of an integer limit. Routine cases, essentially just routine uses of the code, and then challenging cases, i.e. ones that if you were writing the code, maybe you didn't write the code being tested, you might find difficult or error prone. So for the A factor method, some boundary cases, of course, are always going to be the smallest or one of the smallest things that you could input. So a factor of 1. Routine or challenging could be potentially 2 could be difficult because it's a prime number. 4 could be difficult because it's a square. Routine would be pretty much anything that is a routine case. These are your inputs. These are potential results, and then you have a reasoning behind it. So decrement, an example of a boundary case would be 1 because that is the smallest possible value that you can input into the decrement method. A routine case would be like 2. 10 would be pretty challenging because you're trying to, or you have to deal with the fact that you're going from 2 digits to 1 digit. And if it's a recursive implementation, it's not as easy as you might think. And then a routine case would be passing in something like 42. All right, what about this boundary case, which is on the illegal side of the boundary between legal and illegal inputs? This would be something that you do not have to test because if you go back to the contract, it requires that n is greater than 0. So you will never have to test an input that falls outside of the contract. If you go back to our Venn diagram, this is the diagram that you want. It's never needed to test something that's outside of that outer circle because it's never something that's actually allowed by the method contract. In fact, I would be more worried if it looked something like, oh, well, no, it would be like this. Where if you pass in something and it works correctly, but it's not allowed by the method contract, then that means your code is wrong and you should fix it. Okay. Boundary case. This test case is worthless. Wow. Harsh. It violates the requires clause, so it cannot possibly reveal a defect in the method body. Why not? Because natural numbers cannot be negative. That's a brief overview of testing as it pertains conceptually to this class. The biggest takeaways are that when you're writing your test cases, you should have these 3 types of test cases: boundary, routine, and challenging. And yeah, you should take on a different personality and be paranoid and anxious when you're testing. Real advice from OSU CSE. Any questions on testing? All right, now we're going to talk about how it actually happens in the real world in terms of JUnit. JUnit is a testing framework. I'm going to erase this, by the way. 5, 4, 3, 2, 1. Okay. JUnit is what is known as a Java framework. So instead of, say, creating a new Java project and you have to fill everything in, it kind of has a template for you to fill in. It's like it's like one of those color by numbers things. You get the test fixture and you just have to populate it with test cases, and then you can run it and Java takes care of everything for you. Primitive testing. First, we're going to talk about how you might test in other ways which are bad. Not bad, but if you wanted to test your code without using JUnit or without using a test fixture, how could you do it? Well, one way would just to be using main as a command interpreter with a console input and output, allowing the user to enter in inputs and then printing out the outputs. And then the user can use their discretion to determine whether or not the inputs correspond to the correct outputs. This is simple, easy, and intuitive. It is tedious, error-prone, and not automated. So this jumble of code simply gets a command input. Let's see, if it's I, then it calls the increment method. If it's D, it calls, I think, the decrement method. And what you can do, it doesn't even show you, is you could simply test the code. You could try 0, see if it prints out 1. You could try 10, see if it prints out 9, so on and so forth. But this is not standardized. This is simply trying to look to see if your methods are correct. Another way you could do it is you could write main to contain sets of inputs and expected results in parallel arrays of argument values and expected results, which has been done in some of the earlier labs, and then simply write a loop in main which compares the actual results to the expected or allows results. So here's an example of that. You have numbers, you have roots, and then you have the results. So how it works is these are parallel arrays. So all of their indexes line up. So 0, that's the wrong side of the chart. The first root of 0 is 0. The second root of 0 is 0. The third root of 0 is 0. The first root or the second root of 1 is 1, and so on and so forth. And what you do is you loop through and you grab the number, the root, and then you store that in X, and then you check to see if it is the same as a result. Else you print out that it failed. And this is a better way to do it as it is automated, and you can add more test cases by simply adding in the number, the root, and then the result to this integer value here, or this integer array here. However, you need to be able to write the values of the arguments and the expected results using Java literals in the array initializations. It gets a lot more annoying if suddenly the root method has to be written using natural numbers, and then you have to make however many natural numbers, or you have to write a while loop that initializes natural numbers for each number. A lot more complicated. Which does not work for some types, where each set of input values and or expected results must be created by performing a series of method calls, i.e. increment, new natural number, etc. Another drawback is that if you allow multiple results, how do you choose which one is correct? So if you're trying to test that A factor method using this, what do you put in the results array? Because it can return multiple things. So now finally we get to JUnit, which is the testing framework that we will be using. So JUnit is a testing framework. A framework is one or more components with holes in them. So take color by numbers. You fill in the framework with the test cases. The result of combining the framework and the programmer's code, i.e. the test cases that you will write, is the complete product. Here's an example of a skeleton of a JUnit text fixture. You'll notice it looks a lot similar to Java classes. However, you have this @test annotation above each of your tests. And what this does is it tells Java, hey, this is a test case. There are going to be what are known as assert statements within them. And Java actually opens up a separate view where it lists all of your test cases. And if you run the test cases, it will highlight green if it's correct. It'll highlight red if it's not. It's a very, very awesome, because when you write out your test cases and then you run them and they all go green, it's like a hit of dopamine. So if you wanted to test the root method, say you wanted to test what the third root of 1327 root 3 was, this is typically the naming convention for it. And then all you have to do is you have to add this @test annotation above the method. The imports that we're putting in, assert is something that we will use often. Essentially, it's a way to force the user to prove that something is true. So if you say that say you have the A factor method and you call the A factor method on something, A factor 12, 3, or sorry, A factor just is in one thing. Let's just do 1. This is one factor, 1 as well. So int R for result. What you can do is you can do something like assert equals. You can assert that what is resultant from your A factor method is the correct answer, which would be 1. And if it isn't, then Java will fail the test case, and you'll be able to see it in Java's or JUnit's test fixture. And then test just allows you to test your code. A test plan or a test fixture is a public class with one method per test case. So this class, natural number root, seems to be, based on what I can tell, is a class which implements the natural number root method. You'll write test cases for a bunch of other things. Let's say you were making a calculator that was based on natural numbers, and you had methods like increment, decrement, divide, multiply. Your test class for that might say, or might be named calculator test if the main class is named calculator. The general convention is whatever the class that you are testing is, you just add test afterwards. So, and this is what a test case looks like. It is a lot less scary than you might think, trust. Each test case is a public void method with no parameters, because you don't want to pass anything in. All of the values, the expected values, and the things which you multiply, divide, add, whatever you're doing to test, are defined within the method. Each test case has a test annotation before it, which tells JUnit, hey, this is a test case, treat it as such. And then an easy way to copy and paste test cases is just take this whole thing and copy and paste it, because oftentimes the methodology for setting up your values and setting up your results is the exact same. Okay, there's no like good slide where everything isn't covered, but I guess this is it. Essentially what you do is you create a new natural number, you get the expected value, you create a natural number, you get you create a natural number for the result, your expected result, root, expected root. Oftentimes, if you look at the, I don't think they have the contract. The contract is a good way to test or to check what things you have to make sure are the case. So oftentimes the returns clause will tell you a thing that you have to check. If you have a value or a parameter, which is restores mode, then you have to make sure that it's the same before and after. If you have a clears mode parameter, then you have to make sure that the value is cleared after. And that's where you get into our expected. And then finally, at the bottom of all of your test cases will be these assert equal statements, which assert that the expected value that you should get from the root method is equal to what actually is returned based on the natural number root method. Okay, so some review. A test case exercises a single unit of code. It's normally a method, and a test case normally makes one call to that method. Test cases should be small and independent of each other. So this goes back to the idea of separating out unit tests from integration tests from system tests. When you're writing unit cases or unit tests, as we do in this class, it should only be testing one thing at a time. So an increment method should only be checking to make sure that the natural number is incremented. You shouldn't be trying to test multiple parts of your calculator. That would be more of a system test or an integration test. You only want to test typically one method of your class at a time. A test fixture exercises a single class. It is a collection of test cases, and it is a class that contains @test methods. Tomorrow's lab is all about testing. I would highly recommend not skipping that one. Okay. A JUnit assertion is a claim that some Boolean valued expression is true. Expressions come back into the mix here. Normally, a comparison between expected and actual results, i.e. the dot equals method says that they are equal to each other. So that's what's happening here. What we're basically doing is we're saying one dot equals on. And what we want is we want that statement to be true. Passing a test case is a JUnit version where all of your assert statements, not just one of them, all of the assert equal statements are true. Failing a test case is false when even one of these assert statements does not return true. Okay, so when it's executed, separate instances or objects are created. JUnit creates one instance per test case. And so each, say, a factor test case, use the example that's on here. Each of these test cases that you have, and sometimes you will have upwards of 20 to maybe 30 to maybe 40, depending on how thorough you want to be with your testing, is a new object in the JUnit test fixture, and it runs them in any order. So do not rely on the order of them. They will show up randomly in the JUnit test fixture. The two most useful static methods in the assert class are to check that something is either true, so assert true, or so two things are equal, so assert equals. So oftentimes you want to make sure that potentially a Boolean expression is correct, or oftentimes you want to make sure that two things are equal to each other, whether that be two natural numbers, two integers, two strings, et cetera, et cetera. There's rarely a reason to use any of the other assertion static methods in the assert class. You will typically only use assert equals and assert true. When we get into different collections, like let's say you were testing well, I guess you can't modify XML trees. We'll get into collections like arrays. Oftentimes you want to make sure that the length of your set or your stack or your queue is equal to some expected value. You want to make sure that the first value, or say the top or the bottom of the stack, all the stuff we'll get into is what you expect it to be, but that's actually too much right now. Essentially, assert equals and assert true are what you want to use. If you're worried about an infinite loop, if you run your code and nothing is happening, but you see that it's running, potentially you have an infinite loop in your code. A good way to change this is you can have a timeout after the test case. So you write @test, the annotation, and then you set the timeout equal to 100. And I believe it'll run for 100 milliseconds. So how do you know what is long enough for a test case to run? Well, that's discretion. It's up to you. All right, so some best practices: keep JUnit test fixtures in the same Eclipse project as the code, but in a separate source folder. So usually regular code is in the SRC folder. The test cases are going to be in the test folder. Tests are then included when the project is built, and it helps keep test fixtures consistent with other code. The name of the class is typically the name of the class that you're trying to test, and then the word test afterwards. And then the name of the test cases are simply test, the name of the method that you're trying to test, and then potentially any inputs that you have. So this, if you look at the test case, should be based on what it is named, would be testing the foo method with an input of 13. Do not just name your tests test 1, test 2, test 3, because it's not giving somebody who is just reading the test cases and has not actually written them any indication of what you're actually trying to test. Here is finally a good example of a test case with no annoying callouts above it. So you set up the variables and call the method under test. So we're saying that n is a new natural 1327. This is what we're going to be calling the root method on. The expected value afterwards, as n is a restores mode parameter, is 1327. The root, what we're calling the third root on 1327, is 3. And since it is a restores mode parameter, it has to be the same afterwards. And then finally, the root is what the result is after we call the root method. So we call the rth root of n. That expected value is 10. And then finally, we have our assert equals. So a lot of times people forget to test whether or not variables which are restores mode parameters are the same afterwards. So even though it might seem trivial to test to make sure that potentially the code didn't mess with the natural number on which you're calling the root method, you still have to do it. Sometimes you can write the expected value directly. You don't need to set up a variable for it. So you don't need to make a expected k. You can simply inline the integer literal in the assert equal statement, because it would be kind of pedantic to make an int k expected equals 7 and then pass in k expected. You can, if you want to keep things concise, and that way you can change k expected if you suddenly decide to change the test case, but it's not required. You could also inline something like, instead of n expected, it was assert equals new natural number 1327, new natural number 3, and then new natural number 10. But in this case, it's probably better to put them in separate natural numbers. Here's an alternative test case style, so one that is different than simply just using integers or natural numbers. We have test divide by 10 non-zero. So this tells you everything that you need to know about what you're doing. You're testing the divide by 10 method on a value which is not 0. So you're making a new natural number 1327. You're saying int k equals n dot divide by 10, and then you're asserting equals that the value of n afterwards, as it is now divided by 10, is 132. And then you're testing that the remainder after dividing by 10 is 7. This is another way you could do it. A way that this would be useful is, say, you're working with natural numbers which are greater than the integer limit. And so instead of asserting equals, say, a new natural number which has just a bunch of things, you can use strings as well. It's up to you. A lot of personal preference. Okay. Any questions? That was a lot of information. Any questions on test cases? Okay, spring break started early. Tomorrow's lab is asynchronous. Please do not show up. I will be on Slack pretty much all day, probably until like 8 p.m. So if you have any questions about testing, please reach out, and I will be active on Slack. Have a good spring break.